A modern ship crossing open ocean can check its exact position from a phone, a satellite receiver, and a screen showing a blinking dot on a map, all without ever needing to see the sun, the stars, or the horizon. Now, picture crossing the same open ocean 1,000 years ago, far out of sight of land, under a sky solid with cloud for days at a time, with no magnetic compass yet in use in northern Europe, and somehow still holding a course accurate enough to reliably hit a specific fjord on the other side of the North Atlantic. That is roughly the navigational problem Norse sailors faced on the open water route between Norway, Iceland, and Greenland, and for centuries the only clue anyone had about how they might have solved it came from a strange object mentioned almost in passing in a handful of medieval Icelandic texts, a sólarsteinn, a sunstone. The clearest literary reference appears in Rauðúlfs þáttr, a short Icelandic story preserved in manuscripts from the 14th and 15th centuries, describing an episode involving King Olaf II of Norway. In the story, the king is unable to see the sun directly through a thick, snowy, overcast sky, so he holds up a sunstone, looks through it, and is able to determine the sun's position anyway, using it afterward to confirm that a wise man's separate estimate of the time was correct. It is worth being upfront that Rauðúlfs þáttr is a heavily allegorical text, and the specific scene is widely read as a religious metaphor rather than a technical manual. But a second, less symbolic reference appears in the 13th century Hrafns saga Sveinbjarnarsonar, and church and monastery inventory records from medieval Iceland separately list sunstones as real physical objects being kept and used, which suggests the underlying idea, a stone that reveals the sun's position under an overcast sky, reflected an actual practice, even if the surviving stories about it were dressed up in symbolism. The physical explanation didn't come from historians. It came from a mineral called Iceland spar, a naturally occurring, optically clear form of calcite found in large, gem-quality deposits in Iceland, which has an unusual property called birefringence. Ordinary light passing through the crystal splits into two separate polarized beams, traveling at slightly different angles, and by rotating the crystal and watching how the intensity of those two beams shifts relative to each other, it becomes possible to detect the polarization pattern of skylight. The same faint pattern bees and some birds use to navigate and use it to locate the sun's position even when the sun itself is completely hidden behind cloud, fog, or already below the horizon at twilight. That would remain a plausible but unproven theory if nobody had ever actually found one of these stones in a navigational context. Then, in 2002, a diver working with the Alderney Maritime Trust recovered a chunk of clouded, whitish calcite from the wreck of an Elizabethan-era English ship that had sunk off the Channel Island of Alderney in 1592, found lying close to a pair of navigation dividers among the wreck's other equipment. Magnetic compasses were already standard equipment by the late 16th century, but they were also known to malfunction near the iron fittings and cannon increasingly common aboard ships of the period, giving sailors a very practical reason to carry a working backup method for finding the sun. In 2011, a physicist named Guy Ropars at the University of Rennes in France ran a direct experiment on that recovered Alderney crystal, striking it with a beam of partially polarized light and rotating it to find the single precise angle at which the crystal's two output beams matched in intensity, a method that functions as a kind of depolarizing sundial. Ropars' team, publishing their results in the journal Proceedings of the Royal Society A, found that the technique could locate the sun's position to within about 1% of its true bearing, even under heavy cloud cover, in fog, and even shortly after the sun had already dropped below the horizon into twilight. Conditions where a direct visual sighting would have told a sailor nothing at all. None of that, on its own, proves Viking Age sailors, centuries before that 1592 shipwreck, were actually using the technique at sea, since no confirmed sunstone has ever been recovered from an actual Viking ship burial or wreck. What it does establish is that the physics genuinely works. Using a mineral the Vikings had direct access to in Iceland, described in terms that match how the stone would need to be used. That gap between a technique that provably works and direct proof it was used on Viking-era voyages specifically is exactly what a pair of researchers at Eötvös Loránd University in Hungary, Gábor Horváth and Dennis Saz, set out to test computationally in 2018. Rather than testing a single crystal on a single day, their team ran computer simulations of 3,600 separate simulated voyages along the historical open water route from Bergen in Norway to the Hvarf headland in Greenland, varying the type of crystal used, calcite, cordierite and tourmaline, the level of cloud cover, the time of year between the spring equinox and summer solstice, and critically, how often a navigator stopped to check the Sunstone and correct the ship's heading. The results were sensitive to that checking frequency, in a way that reads almost like a lesson in disciplined procedure rather than raw technology. When simulated navigators checked their Sunstone only once every 4 hours, the ships reached Greenland successfully only somewhere between about 32 and 59% of the time, depending on conditions. But when they checked everyone to 3 hours instead, maintaining the discipline of frequent correction rather than trusting a single reading for half a day, the success rate jumped to somewhere between 92 and 100%. Cordierite, a mineral also known to occur in Scandinavia, performed the most accurately of the 3 crystal types tested in the simulation, while calcite, the very mineral behind the historical Iceland spar sunstone theory, actually performed the worst of the 3, though still well enough to be genuinely useful when checked often. So the honest version of the story sits somewhere between legend and confirmed history. The literary references are real, but partly allegorical. The mineral genuinely has the optical property required to do the job, demonstrated directly on a recovered crystal from a much later shipwreck. The underlying navigation method has been shown, through both physical experiment and large-scale computer simulation, to be not just plausible, but potentially reliable, provided it was used often and carefully, rather than as a single lucky glance at the sky. What remains missing is the one piece of direct archaeological evidence that would close the loop entirely, a sunstone recovered from a confirmed Viking Age ship rather than a 16th century one. What makes the story worth telling anyway is that it represents something quietly impressive, even in its uncertainty. A civilization without a working magnetic compass, sailing open ocean routes between 3 land masses, separated by hundreds of miles of featureless water, using a piece of naturally occurring rock and an understanding of how skylight behaves that would not be formally described in the language of physics, polarization, until the 19th century. The next time a phone silently locks onto satellites through solid cloud cover without anyone giving it a second thought, it is worth remembering that the same basic problem, finding your way across open water with nothing overhead but grey sky, was once solved, or very nearly solved, by holding up a clear piece of Icelandic rock and patiently watching exactly where the light came through.